Good morning everyone. So recall that in this section 28 we discussed how to find a power series solution of second order homogeneous differential equation, and we have seen that there exists a power series solution only if x naught is an ordinary point. So we can find a power series solution about x is equal to x naught whenever x naught is an ordinary point, which means p of x and q of x must be analytic at x is equal to x naught. Now if x naught is not an ordinary point, we will call it a singular point. Now singular point can be classified into two categories. One is regular singular point. So we say x is equal to x naught is a regular singular point if for the given differential equation y double dash plus p of x y dash plus q of x y is equal to 0, x minus x naught p of x and x minus x naught whole square q of x both are analytic about x equal to x naught. And if the point is singular and it is not a regular singular point, we call it irregular singular point. Let's see some questions. So for example, we need to identify x is equal to 0 is an ordinary point, regular singular point, or none of these. So we will start with the first one. So here p of x is 0 and q of x is sin x. We know that sin x is analytic about x is equal to 0. So it implies x is equal to 0 is an ordinary point. In the second one, p of x is 0 and q of x is sin x by x. Yes. Now this is very important. If you see the expansion of sin x by x, it is actually 1 by x minus x cube by 3 plus x raised to the power 5 and so on. And if you take x inside, there is a factorial also. If you take x inside, it becomes 1 minus x square by 3 factorial plus x raised to the power 4 by 5 factorial and so on. It means that sin x by x has a power series expansion, and therefore x is equal to 0 is an ordinary point. The third case is p of x is 0 and q of x is sin x by x square. Now sin x by x square becomes 1 by x minus x by 3 factorial and so on. So it is not defined at x is equal to 0. It means q of x is not analytic at x is equal to 0. So q of x is not analytic at x is equal to 0, but x square q of x is sin x, which is analytic at x is equal to 0. Implies x is equal to 0 is a regular singular point. And this is the last one. So if you see it, then q of x is sin x by x raised to the power 4. So even x square q of x would be sin x by x square, which is not analytic. We have just seen above at x is equal to 0 implies x is equal to 0 is a irregular singular point. Yes. So moving further, we will see that if x is equal to x naught is a regular singular point, then how can we find its power series solution? So this method is known as Phobinius method, which says that if x naught is a regular singular point of the given homogeneous second order differential equation, then there exists at least one power series solution, which is of the form summation a n x minus x naught raised to the power n plus r. So you can see that it is simply the power series solution which we have seen earlier also, summation a n x minus x naught raised to the power n. I am just multiplying the power series solution by x raised to the power r. Yes, and therefore to write down the power series solution we must find the values of r, where r is a root of the quadratic equation which we call indicial equation, and it is obtained by equating the lowest degree term in x of the equations. We get this equation by substituting the solution into the given equation and then equating the coefficient of lowest degree term to 0. So this gives us an indicial equation which would have quadratic equations. It would have two roots. Now once it has the two roots, then we claim that the above theorem guarantees at least one power series solution. Why at least one? For example, if the two roots are distinct, we may have two power series solution because I change the value of the r. But let's say the equal roots are there, r is 2, 2. So in both the case I will get the same power series solution. So I am not saying that the differential equation would not have two solutions. We are just saying it would not have two Frobenius series solution. So there is a lot of difference between two things. Yes. So now let's see how do we find the indicial equation. So for this given equation in today's class we will see how to find the indicial equation, and then in the next class we will see how to find the Frobenius series solutions. So to begin with, first check what is your p of x and q of x, which means we need to check that. So here p of x is 3 minus x by 2x and q of x is minus 1 by 2x. So clearly x is equal to 0 is not an ordinary point, but x p of x is 3 minus x by 2 and x square q of x is minus x by 2. Both are polynomial in x, that's why they have the power series solution about x is equal to 0, and it means that x is equal to 0 is a regular singular point. So in case of regular singular point, the solution looks like summation a n x raised to the power n plus r. Now I need y dash and y double dash. So implies y dash is summation n plus r a n x raised to the power n plus r minus 1, and y double dash is n plus r n plus r minus 1 a n x raised to the power n plus r minus 2. Now we always write the summation from 0 to infinity, especially in case of regular singular point, because it depends on the values of r. For example, if r is minus 3, then the first term would be x raised to the power n minus 4. It means that n must start from 4. But for example, if r is 2, then it becomes x raised to the power n plus 1. It means there is no problem if it start n from 0. So since we do not know, and if x has the negative powers, so those coefficients would be automatically 0. Therefore it is safe to write down the summation from n is equal to 0 to infinity. Now let's substitute the values. So it is 2x, so 2 summation n from 0 to infinity n plus r minus 1 a n x raised to the power n plus r minus 1. It is minus 2, but I multiplied by x because 2xy double dash is there, plus 3y dash, so a n n plus r x raised to the power, then minus x y dash, so a n n plus r and x raised to the power n plus r, minus y, so a n x raised to the power n plus r. Now for the indicial equation we need to equate the lowest degree term to 0. Yes, so equating And what is the lowest degree term? So you can see that n is always starting from 0. So if I put n is equal to 0 in all the 4 terms, then in first 2 term the coefficient is x raised to the power r minus 1, and in last 2 term it is x raised to the power r. So it means x raised to the power r minus 1 is the lowest. So equating coefficient of x raised to the power r minus 1 to 0. So that gives me, from the first term I will get 2, then a naught r minus 1 plus 3 a naught r, and in the last 2 term it is start from x raised to the power r. It means there is no coefficient of x raised to the power r minus 1. Now recall that whenever we write the Frobenius series solution, we assume a naught is not equal to 0. So since a naught is not equal to 0, I have 2r square minus 2r plus 3r is equal to 0. That gives me r is equal to 0 and minus half, which are the roots of the indicial equation. Let's quickly try one more question. 2xy double dash, so summation a n plus r minus 1 x raised to the power n plus r minus 1, because it is multiplied by x, plus xy dash, so n plus r and x raised to the power n plus r plus y dash, so a n plus r x raised to the power n plus r minus 1 plus a n x raised to the power. Again equating the coefficient of x raised to the power r minus 1 to 0. So if you equate it, you will get, from the first term you will get 2 a naught r minus 1 plus, in the second term there is no coefficient of x raised to r minus 1, in the third term it is a naught r, and again in the last term it is not there. Now a naught is not equal to 0 implies 2r square minus 2r plus r is equal to 0. So that gives you 2r square minus r is equal to 0. That gives you r is equal to 0 and half. Yes. So this is the method to find the indicial equation. But sometimes we just need to find the indicial equation. If we have to find the complete solution, then we must follow this method, because from the equation which we obtained by substituting solution into the given equation, we can easily compute the recurrence relation. And if we consider the coefficient of x raised to the power lowest degree term to 0, we will get the indicial equation. But let's assume that we just need to find the indicial equation. So in that case, to save our time, there is another method. So this method says that let the general equation with a regular singular point at x is equal to 0 looks like x square y double dash plus x p of x y dash plus q of x is equal to 0. Yes, so let's say I have the equation of this form, where p and q are analytic at x is equal to 0. So I am just proposing this method to find the regular singular, to find the indicial equation only about x is equal to 0. The previous method is more generalized, but it may take a little bit more time if we just have to find the indicial equation. Since p and q are analytic, therefore there is a series, power series expansion for p of x and q of x, and x is equal to 0 is a regular singular point, therefore y of x is x raised to the power r summation a n x raised to the power n. If I substitute all the values, then it becomes my y double dash is n plus r minus 1 a n x raised to the power n plus r minus 2, but it is multiplied with x square, plus xy dash is there, so n plus r a n again x raised to the power n plus r and px, which is pn and x raised to the power n, then y is there, an x raised to the power n plus r, and qn x raised to the power n is equal to 0. Now the lowest degree term is x raised to the power r, so equating coefficient of x raised to the power r to 0, it becomes a naught r minus 1 plus, from the second term again I will get a naught r, and from the summation I need x raised to the power 0 only, so therefore I take p naught, and from the last one I take a naught and q naught is equal to 0. Now a naught is not equal to 0, so this becomes r square plus p naught minus 1r plus q naught is equal to 0, which is the required indicial equation where p naught is p of 0 and q naught is q of 0. It means that if I can transform the given equation into the form x square y double dash plus x p y dash plus q y is equal to 0, then about x is equal to 0, I can directly use the formula that the initial equation would be r square p naught minus 1r plus q naught is equal to 0. Let's see the question to better understanding. So now this is the given equation which we have already find the initial equation, but using this method I must multiply it by x and divide it by 2. So it becomes x square y double dash plus 3x minus x square by 2 y dash minus xy by 2, or I can write it as x square y double dash plus 3 minus x by 2 xy dash minus. So now if you compare it with this one, then it is x p of x. So therefore my p of x is 3 minus x by 2, which means p of 0, which is p naught, is 3 by 2. And similarly q naught is, it is minus x by 2. So if I put x is equal to 0, q naught is 0, because q of x is minus x by 2. So now the given equation becomes r square plus p naught minus 1r plus q naught is equal to 0. That gives you r is equal to 0 and minus r. So you can see how quickly we managed to compute the initial equation. Similarly, if I see this question which we already discussed, again multiply by x and divide by 2. So it becomes x square y double dash plus x plus 1 by 2 xy dash plus 3x by 2 is equal to 0. So p naught is 1 by 2 and q naught is 0. Here y is there. Q naught is 0, therefore it becomes r square plus p naught minus 1r is equal to 0. That gives you r is 0.5. So in today's class we have seen that how to find the initial equation, its roots. Now based on the roots there will be 4 cases to find the Frobenius series solution. So we will discuss 2 cases in the next class and then 2 more cases in the coming classes. Thank you.